Well, hello and welcome to the last and final lesson of Activity 22. We are on lesson 22-4, solving right triangles. And so for the last few lessons, we've been exploring these three major trigonometric ratios, also referred to as functions, as we saw in the last lesson, the sine, cosine, and tangent ratios. So let's look at our learning target here and see what is ahead in lesson 22-4. Our task is to calculate angle measures from trigonometric ratios. Up until this point, primarily, you've been given the angle measures and you were asked to find a missing side based on a trigonometric ratio. Now, we're going to figure out how to use those trigonometric ratios to calculate angle measures. And then, just like always, we're going to continue solving, in this case, solving right triangles. So we're going to see exactly what that looks like in terms of solving a right triangle now that we're finding our angle measures. So we're actually going to chunk for this lesson items 1 and 2 together. So go ahead and draw a line at the bottom of this page 315. And go and read the text, answer items 1 through 2 before playing through the video. So hopefully you took a second to really explore some unique ideas that this lesson is presenting. First and foremost, number 1, in a right triangle, again, that's really primarily what we're looking at right triangles. Triangle ABC with an acute angle A, you know that the sine of A is equal to the square root of 3 over 2. In other words, in reference to angle A, the side opposite of it can be represented as the square root of 3, as long as the length of the hypotenuse can be represented as 2, because the sine trig function, the definition, is the opposite leg over the hypotenuse. So, draw a possible right triangle where this is true. Now, this is probably the simplest one to do. Remember, you could have actually taken this triangle and dilated it by any scale factor, and those two triangles would be similar, therefore they'll have this same ratio. So I just kept it pretty simple here and said, if the sine of A is square root of 3 over 2, then drawing a right triangle, ABC, opposite of angle A, the length from B to C should be square root of 3, or any multiple of square root of 3. And the hypotenuse, which in my case was BA, has to be a length of 2. Now, B said determine what must be true about angle A using what you know about special right triangles. Well, there's two special right triangles, the 45-45-90 and the 30-60-90. But before I just declared that it had to be the 30-60-90, I wanted to make sure that these really are those special measurements that we found with the 30-60-90. So I plugged in the two sides that I knew, plugged those into the Pythagorean theorem to find this third side. So the side I was missing, AC, I called it lowercase a because it's one of our legs. I plugged in BC, the other leg, as B. And of course, BA, the hypotenuse, I plugged in as C. A squared is still A squared. Square root of 3 squared, interestingly enough, is the square root of 3 times itself, which is just 3. Because if you think about it, square root of 3 times itself is the square root of 9, and the square root of 9 is 3. 2 squared is 4. Subtract 3 from both sides, and I find that A squared equals 1. Well, if you didn't know this, 1 squared is 1, so A is 1. So how did I know this was the 30-60-90? Well, the big selling point here is that the length of this leg is 1 unit, and the hypotenuse is 2 units. And hopefully you recall from that special right triangle that whatever the length of the shortest leg is, the length of the hypotenuse is doubled. And so that's the relationship, the ratio I saw, that this short leg, AC, was half the length of the hypotenuse, which was 2. And the length of the short leg times the square root of 3 is the length of the long leg. So 1 times the square root of 3 is square root of 3. So the measure of angle A has to be 60 degrees, primarily because I knew angle B had to be the 30-degree angle, because opposite of the smallest angle is the smallest side. So the measure of angle B is 30 degrees because AC is 1, BC is square root of 3, and BA is 2. Therefore, it's And I just realized that is not how you spell therefore. So let's erase that real quick. So now that that's fixed, so I realized that it was a 30, 60, 90 because these three measurements. Therefore, angle B had to be 30 degrees. Angle A had to be 60 degrees because it's a right triangle. And remember, angle B and angle A have to be complementary angles. So once I knew angle B was 30 degrees, because it was opposite of this short leg, angle A had to be 60 degrees. Now, in item 1, you're given the sine of an acute angle. We don't know the actual measure, and we're asked to find the angle whose sine is equal to that ratio. In other words, you're finding what's called the inverse sine function. Specifically, this case, the inverse sine function. And the way it's written, a lot like the inverse functions you learn in Algebra 1, sine inverse of square root of 3 over 2 is 60. So notice what's happening now. In the previous lesson, they told us the sine or the measure of that angle, whatever A was, and we found one of the other missing parts of the ratio. Now, we don't know the measure of the angle, and we use the ratio to find the measure of the angle using the inverse function. So it says the expression sine negative 1x is read as the inverse sine of x. For example, just to kind of relate it back to what you learned in Algebra 1, you saw a function like f of x equals 2x plus 3, where the first thing you do is multiply your x times 2 and then add 3. And the inverse function of that is the exact opposite. It's literally going backwards. So the first thing you did here was multiply by 2, then add 3. Then you're going to subtract 3 first, then divide by 2. And so the input becomes the output. And I'll show you. For example, for the original function, let's say if x was 1, plug in 2 times 1 is 2 plus 3, which is 5. And we'll do another one just so you can see how this really works. If we plug in 2 for x, 2 times 2 is 4 plus 3, which is 7. And so the reason inverse functions exist now is we're going to take these outputs from the original function and we're going to plug them into the inverse, and we'll actually get them as the original input. So now I'll take 5 and 7 and plug them into the inverse function, and I should get the original input. So if I plug in 5 here in the inverse function, 5 take away 3 is 2, and 2 divided by 2 is 1. Now let's plug in 7. 7 take away 3 is 4. 4 divided by 2 is 2. And so one of the reasons we learn inverse functions is that based on what we're given, we can produce a new output. And that's really what's happening here. We don't know the measure of the angles now. And so using these inverse functions, look what the inverse sine function will do. If sine of A is equal to x, then the inverse sine of x, the actual ratio, gives us the angle measure. So it's giving us that original input we started with in the previous lessons. Now that is the output. So item 2 says use a scientific or graphing calculator to evaluate each of the following to the nearest tenth and make sure your calculator is in degree mode. So I'm going to show you using the Desmos calculator as well as the TI-83, I believe, to TI-83 on evaluating these inverse functions. But before we do that, before I show you the actual calculations, let me just break down what exactly is happening here. I mean, it's a pretty simple process, but let's make sure we actually understand what we're doing. So this right here says the sine inverse of 1/2 is, and I've already provided the answer, 30 degrees. What we're really saying is suppose we had a right triangle. Again, we're dealing with right triangles. We didn't know the measure of this angle right here. Notice it's not even labeled. We know nothing about the measure of that angle. But we do know that when you compare the opposite side to it over the hypotenuse, you get the fraction 1/2. Doesn't necessarily mean the side opposite of it is 1 and the hypotenuse is 2. The ratio of the opposite side to the hypotenuse is 1/2. So how can we find the measure of that angle? Well, if I know the opposite side of that angle compared to the hypotenuse, then I'm going to use the sine function. So Now let's take a look at actually how to find that the fact that the answer is 30 degrees. So I'm going to start by showing you on the Desmos calculator. So we're going to take the sine inverse of negative 1/2, excuse me. So let's just make sure we are in degree mode here. It does say degree, so we're good. And then we're going to go over to the function tool. Not sure why that's still popping up, and then we're going to click on the sine inverse function. So it's the sine inverse of 1/2. So you can put 1 divided by 2 or 0.5. And notice that they tell us that the sine inverse of 1/2 is 30. And again, what that's telling us is the actual angle measure. Now let me show you how it's done on the TI-83, just a little bit different. So let's get it turned on. Now, we already accessed the sine function before, and if you notice, right above each of these trig functions is actually its inverse. Sine to the -1, cosine to the -1, and tangent to the -1. So to access anything in yellow on this graphing calculator, we're going to first hit this button, the second button, and notice there's a little arrow that pops up. So we're going to hit second sine, and notice that the sine inverse pops up. And you can either put 1 divided by 2 or convert that to a decimal if you prefer, but I'm just going to go and put it in as a fraction, 1 divided by 2, close parentheses, and hit enter. And notice it gives us the same thing that Desmos does. So the inverse sine of 1/2 is 30 degrees. And we can repeat that process over and over again. But let's just make sure we understand what's actually happening. So now I have just discovered, because the opposite side of this angle, when compared to the hypotenuse of this angle in this triangle, this angle has to be a 30-degree angle. And so that's what we're actually doing here. We're using these ratios to now find the missing angle measures. So we just calculated those angle measures, which is learning target 1. And notice what it says here, using known measures to find all the remaining unknown measures of a right triangle is known as solving a right triangle. So now, if we're given any measurements and we solve for all of the other unknown measures, that's referred to as solving the right triangle. So let's explore our second learning target. So Tricia designs the logo shown for one of her clients. She needs to know all the missing dimensions and angle measures of the logo. So anytime we find any unknown measure, or not just any, I should say all unknown measures of a right triangle, it's known as solving the right triangle. So here in these next few problems, we are going to complete our second learning target. So we're actually going to chunk 3, 4, 5 together, and they break it down how to first begin finding every unknown measure. So read through 3, 4, and 5. Try to complete those on your own before playing through. Okay, so item 3, the first task that we have, or that they give us, we could have honestly found QR at this point because we have 2 of the legs of this right triangle. So we could go ahead and find the hypotenuse using the Pythagorean theorem, and that is item 5. But they wanted us to find the measure of angle Q first. So we're going to use, anytime we're finding an angle measure, we're using an inverse trig function. So let's talk about what we have and why I landed on the tangent function. So looking at angle Q, I actually know the side, or the measure of the side opposite of it, SR, which is 65 millimeters. So I know the opposite leg to that angle. And I've also been given the length of SQ, which is 33 millimeters, and that side is considered adjacent to angle Q. So the trig function that utilizes the opposite leg and the adjacent leg is known as the tangent function. So go back to our previous lesson where we can say that the tangent of angle Q is the opposite side, 65 over 33. Now, if our goal is to find the measure of angle Q, we're going to use the tangent inverse of that ratio to find the measure of the angle. Notice our final answer is in degrees. So Just to reiterate how to do that, we go over to Desmos. We're just going to, for example, you can already see the work here done on tangent inverse of 65 over 33. But the way you do that is I'll actually get rid of that if you want. And I'll click on Functions, Tangent Inverse. It's wanting to do it all together. Let's start a new one. Tangent Inverse, and we'll just type in 65 over 33. And we get roughly, rounded to the nearest 10, 63.1, because the 8 tells the 0 to round up. So we found the measure of angle Q is 63.1 degrees. Well, hopefully you're imagining that we can do that exact same process to find angle R. So in item 4, it says, describe 2 ways to find the measure of angle R without finding the length of the hypotenuse. So you might be wondering, well, of course, why would I need to find the hypotenuse? Well, if you found the hypotenuse first, then you could use some other trig functions. But if we're trying to find the measure of angle R based on what we already know, we're going to use the tangent function again. But now our ratio is going to look a little different. Notice it's the inverse of the previous ratio because the tangents of complementary angles are reciprocals. So if R is the indicated angle, the opposite side to angle R is SQ, and that is 33 millimeters. Put that on top. And then the adjacent side to angle R is side SR, which is 65 millimeters. That's why I put it on the bottom, because definition of tangent is the opposite side to the adjacent. And so again, if the goal is to find R, in this case, the measure of angle R, then we're going to take the tangent inverse of that ratio, and we found 26.9 degrees. Now, obviously, that's not the only way to find angle R, because we know, once we know angle Q, these 2 angles have to be complementary angles, which means they have to add equal 90 degrees. So that math is clearly easier and a route that I would definitely encourage, but although it's great to see that the tangent of R still gives us that same measurement. So regardless, we found that the measure of angle R is 26.9 degrees. So now we know all 3 angle measures, and we know 2 of the sides. So we need to just find one more side, in this case the hypotenuse, and we will have solved the right triangle. So item 5, they want us to describe 2 ways to find the length of the hypotenuse. Now, I didn't necessarily describe the 2 ways. I actually showed the 2 ways. So method 1 to find the hypotenuse is using the Pythagorean theorem, a squared plus b squared equals c squared, where c is the length of the hypotenuse. So that is actually what we're finding here. So I plugged in 33 millimeters for A, 65 millimeters for B. Remember, it doesn't matter. A and B are just the length of our legs. Regardless, if you were to put 65 squared first or 33 squared first, you're still going to get to this sum, 5,314. Unfortunately, 5,314 is not a perfect square, because when I take the square root of 5,314, I get a decimal. And so roughly the length of QR, the hypotenuse, is 72.9 millimeters. The other method I wanted to show is the method we learned in the previous lesson, that we can use the sine of that angle and write a ratio, the exact opposite of what we're doing here. That's why they call it an inverse function. So first angle we found was angle Q. So I'm going to use that 63.1 degree angle. And I was told the opposite side of angle Q, which is our 65 millimeter. And we were asked to find the hypotenuse. So that is the sine function, comparing the opposite side of an angle to the hypotenuse of that angle. So the sine of 63.1 degrees is the opposite side, 65, over the hypotenuse x. I found the decimal approximation to the sine of 63.1. Let me just remind you how to do that again here. So we're not actually going to use the inverse function because we're not finding an angle. We already know the angle. So sine of 63.1. And again, we're going to round to the thousandths place, which the 1 is in the thousandths place. So the 7 actually tells the 1 to round up. So, like I said, sine of 63.1 is roughly 0.892. We're going to write this side now as a ratio by putting it over 1 and then cross multiply. In fact, we'll have to cross multiply and divide here to then find that just like we did with method 1, we found that the length of the hypotenuse is 72.9 millimeters. So last but certainly not least for this lesson, let's take a look at the check your understanding. So we're actually going to chunk those two items together. So go and take a look at items 6 to 7. Provide your best answers, your reasonable answers before playing through the video. So items 6 and 7, definitely great follow-up questions to actually to the entirety of activity 22. So item 6 says, what is the minimal amount of information needed to solve a right triangle? Remember that what we're really meaning when we say solve a right triangle is find any unknown measure. So there's actually two possibilities here. The first possibility is if we know two sides of that right triangle. Reason being is if we know two sides of that right triangle, we definitely can find the third using the Pythagorean theorem. So if I know A and B, I can use the Pythagorean theorem to find C. Secondly, once I know all three sides, I could then use our inverse trigonometric functions to find these other two angles. For example, if my goal was to find the measure of this angle here, I could honestly use any trig function now that I have all three sides, but I could find the sine inverse of, let's say, opposite, which would be A, of that indicated angle to the hypotenuse C, and that actually would find this indicated angle here. Likewise, to find this angle, I could use any of the trig functions again because I found all three sides. Or once I found the angle, this angle here using the inverse sine function, I know these two angles have to add equal 90 degrees. So if I know two sides, I can use Pythagorean theorem and the inverse functions to find the two missing angles in the third side. Now the second method, if we knew the length of one side and an angle measure, one of the acute angle measures, we could find every other side. Now we can't use Pythagorean theorem from the beginning because we only know one side length. But if the goal is to, let's say, find the length of the hypotenuse C, well, this side that I'm given is actually adjacent to the known angle measure, and I'm looking for the hypotenuse, so I could actually do the cosine of whatever angle I'm given equal to the length I was given over what I'm trying to find, which I guess we could call C. And once I find the length of the hypotenuse using that function right there, I now have two of the sides. Well, once I have two of the sides, I can find the third using the Pythagorean theorem. And knowing this angle measure, these two have to be complementary. So once I know that angle measure that was given, I can subtract it from 90 to find this angle measure. Now, item 7 really is just trying to make sure we understand what we're doing in this context. So it says, explain the difference between the two expressions, sine of 15 degrees and sine inverse of 0.2558. Well, if you actually go over to Desmos and type in the sine of 15 degrees, I'll show you. The sine of 15, you actually get that decimal that they gave us. But it was written as the sine inverse. So the whole entire idea of these inverse functions is to take a new input and produce a new output. Back in the previous lessons, we were given an angle measure, and we used the trig ratio of that angle measure to find a missing side. Now, we don't know the measure of the angle, but we do know the ratio of two sides. For example, in this case, A over B. We know the length of two sides, a ratio, and then we can use the sine inverse of that ratio to find the angle measure. That's why you see here the sine of 15 degrees is 0.2558, and the sine inverse of 0.2558 is 15 degrees. So let me try to explain it in context, what we're seeing here. For example, we have this little right triangle here with a known angle measure of 15 degrees. If I say the sine of 15 degrees is 0.2558, what I'm really saying is that any side opposite of a 15-degree angle in a right triangle, any side opposite of that angle compared to the length of the hypotenuse is going to be that decimal. In other words, sine of 15 degrees is A over C. And regardless of whatever the length of A is, some number, when it's put on top of C in fraction form and then rewritten as a decimal, it's going to be that decimal. Because similar right triangles have corresponding sides that are proportional. And that's what this really is. It's a ratio. And that's what proportional means, ratios that are equal. So if that's true, if the side always opposite of the 15-degree angle when compared to the hypotenuse is that decimal, then if we know that ratio to begin with, if A over C is that decimal, then the angle opposite of that leg, has to be that 15-degree angle. So we're using functions and inverse functions to solve right triangles. And recall, as we close out this activity, that solving a right triangle is finding any unknown measures. And there's tons of different ways to do it, especially what we saw here in items 3 through 5. Well, that is the end of lesson 22-4. That is actually the conclusion of activity 22. As always, please complete the lesson practice. Great practice of all the skills we're learning and how to piece them together. And as always, go back to your learning targets and reevaluate your understanding in hopes that your understanding improved. Anyway, thank you all for watching.